Hello, everyone. Thanks for attending this annual webinar. Today we have the pleasure of having Fedor Sinkovic here with us. Fedor is professor at the Comenius University. He's a member of several experimental collaborations, such as Juno, BICAL-DVD, NEMO, and Legend, all involved with neutrino physics, neutrino oscillations, neutrino double band decay. And he's going to tell us about masses, oscillations, and nature of neutrinos. So thank you very much, Fedor, for accepting our invitation. And please go ahead with your seminar.
Good afternoon, everybody. I want to thank for kind invitation to give this seminar about the subject I'm working on, even together with Sergey Kovalenko for many years already. So part of the results which I will present, we obtained together. So I now share the screen. And I'm starting. Can you see my screen?
Yes, we can see.
Yes, yes.
Yes, and even my cursor?
Yep, yep.
Oh, great. So everything is working. So in my talk, I will speak about problems of neutrinos, about the neutron masses, oscillations, and about neutrinos of beta decay. That's meaning about the nature of neutrinos, which can be Dirac or Majorana. After some introduction, I will tell you the current status of the experiment looking for neutrinos double beta decay. I will mention a possible mechanism of generation of neutron masses, which is different from that we know from other charged lepton and quarks. And then I will even address a possibility for look for new physics with two neutrino double beta decay. I will discuss the nuclear and even atomic structure problems related to neutrino double beta decay, and I will maintain the importance of supporting nuclear experiments to solve the problem of the value of weak axion coupling constant and even nuclear and to fix the value of nuclear matrix element and its uncertainty. So you know, neutrinos are everywhere, and so we know that it is the most abundant particle in the universe, and there is a huge amount on these relic neutrinos, but we have not seen them because we don't have technology to see them till now. We already detected, mankind detected the solar neutrinos, which are in the sun, atmospheric neutrinos, reactor neutrinos, those neutrinos which are created in the atmosphere of our planet due to cosmic rays interactions. And also we know there are also ultra-high energy neutrinos because of some accelerators, cosmic accelerators in the universe. So there is large spread of energies of these neutrinos, and we need different technologies for different of them. Just to mention to you that you know that we need about sorry, I forgot to switch off. Nemôžem teraz, lebo mám prednášku. Sorry, I just switch off it. And that, for example, our planet is not more transparent for ultra-high energy neutrinos of the PV from the PV region. On the contrary, we need about medium of with the width of 1 light year to capture atmospheric neutrinos. This light is. So why we are interested in neutrinos? Because neutrinos can tell us something about the origin of the universe and about the related problems, and also what is happening in the universe and the stars, about the evolution of the universe. So if we would detect relic neutrinos, we have more information what was at the beginning of the universe. Neutrinos with possible CP violation in neutrino sector can explain the difference of matter and antimatter in the universe. We know that we see only matter in the universe, not antimatter. We know that neutrinos constitute dark matter of the universe, about 1% from the 24%. And neutrons can help us understanding sun, stars, supernova explosion, and so on. So with neutrons, we can study cosmic events like collisions of neutron stars or black holes and something like that. And also geoneutrinos can tell us what is happening in the deep in our Earth, what we cannot find out with other devices or instruments. Currently, we have very successful standard model of particle physics in which we have only left-handed neutrinos, and which is practically complete after Higgs was discovered at CERN. And after neutrino oscillations, the phenomenon of neutrino oscillation was confirmed or just observed in many experiments with solar atmospheric accelerator relic reactor neutrinos. So the main, we know already there is some new physics beyond the standard model, because to explain small masses of neutrinos, it is not possible within the standard model where we have only left-handed neutrinos. By global oscillation of neutrinos data, we got information about the transition from the flavor neutrinos which are created in vertices, particle vertices, with massive neutrinos which are moving in space. This transformation is given by 3 rotations, and it includes 3 mixing angles and 1 CP violating phase. Neutrino oscillation depend also on the mass differences, which are just given by 3 neutrino masses. So we don't still know the absolute scale of neutrinos masses. Here are the parameters. From these parameters, we see that this matrix, so-called Ponte-Kromáky-Nakagawa-Sakata matrix, is not diagonal. It also indicates that the generation of neutron masses might be different from that we know, for other lepton and charge, which is due to Higgs mechanism. The standard analysis, with global oscillation analysis, are performed within the formalism of neutrino oscillations, which were already introduced within the quantum mechanics. And many years ago, when the propagation of the neutrinos was described by plane waves, so we have some source and some detector, and in between there is some propagation, and the probability of transformations from one type of neutrino, one flavor of neutrinos to another, is given by this oscillation probability, which depends on the mixing elements of the mixing matrix and the masses of neutrinos, the distance of propagation, and the energy of neutrinos. So this, the whole oscillation, that means that depends on has 3 parts: production of these neutrinos, propagation, and detection. So it can be considered as a single second order process. This formalism was tried to be improved on the reformulating within quantum field theory. First was Boris Kaiser, who introduce formalism of wave packets. This wave package formalism has some problems with definition of the flavor states, or this problem of the width of these packets, and the coherence of these packets. So there are some open problems, and this formalism was never used for global neutrino analysis of neutrino oscillations parameters. Recently, we look also on this problem and show that it is possible to formulate it also with plane waves using quantum field theory approach, just considering it as one single diagram, the whole neutrino oscillation process from the source to the detector. In that way, we have just a matrix element of the process. We have the part of the associated with the productions, these hadron currents, with the detection also corresponding hadron currents, and propagation, which is given by this lepton currents with neutrino propagator. When we decompose this propagator following the time ordering, of course, we take into account only propagation in time, not opposite. So we have only a real propagation of particles. This neutrino propagator, after integration of energy of neutrino, can be given here, and it contains energy denominator with a pole. So in whole of this matrix element, if we integrate over time variables x10, x20, we get energy conservation for the whole process, which is given by this delta function, and just by the energy denominator. There's a possibility to go forward by considering this pole in the energy denominator, which give us separate energy conservation for the source and also for the detector. And we got just plane wave, and the momentum of neutrino is given, the energy of the neutrinos are related, energy is conserved of the neutrino, and the propagation is given in the distance L connecting the source and the detector. Thus, we can get amplitude of this process, which contain energy conservation and two momenta conservation separately for source and for the detector. With this additional lepton and hadron current parts, yes, which is given here. I think is a misprint. This should be with some B spin-offs are missing, or this momentum should be inside of the neutrino. Nevertheless, new point is that we introduce so-called master formula, which is generally just Fermi-Golden rule for the second order process. So we have normalization of the states with the plane waves, and we have normalization to the different volumes, to source and to detector, and making some symmetrization. So this general formula can be used for calculation any process which includes neutrino oscillation. As an example, we considered pion decay into muon and neutrino, propagation of neutrino, and capture of electron neutrino by neutron, and production of electron. So Here is the standard formula which is used in the quantum mechanics in this part, which you already introduced. So inserting the flux of the neutrinos from the pion decay with blue, here the propagation, and this comes from the cross-section for the neutrino absorption. So this formula agree quite well with our expression, derived by considering this process as the Feynman diagram, but we have some additional terms, which is indicated here. We found out that this formula, due to introduced approximation, is accurately enough for if the mass flow differences are the ratio of mass flow difference to the energy of neutrinos is very small. So we show that one can use this formalism of plane waves also within quantum field theory. Before it was considered that one need to consider wave packets. So it is about neutrino oscillation. So after neutrino oscillation was observed, we know there are 3 families of neutrinos. There are at least 3 massive neutrinos. We know the relation between these flavor mass states. That's been Pontel-Koromaki Nakagawa-Sakata matrix. And there are some still unknown questions. There's still some questions. So we don't know the nature neutrino, whether it's Dirac-Majorana. And we know that as the neutrino is neutral, can be on antiparticle. In that case, we are saying that neutrino is Majorana particle. In opposite case, it is the case like other lepton and quarks, so it is a Dirac particle. We don't know much about the CP evaluation in the neutrino sector. We don't know whether neutrinos are able, whether there are sterile neutrinos, about the magnetic moment, statistical properties, and so on. But the main 3 problems, nature, mass hierarchy, and CP properties, even sterile neutrinos, can be studied with help of neutrino-less double beta decay. So neutrino double beta is possible when neutrino is Majorana particle. That means we have Majorana mass term. And Majorana mass terms can be constructed with the fields we have already in the standard model with the left-handed neutrinos. So one can construct this term, which is 5-dimensional operators. And we assume that after some spontaneous symmetry breaking, we get just effectively this operator is 5-dimensional operator. And if we would assume just we would assume that the current constraint of the mass of neutrinos, of the heaviest mass of neutrinos is less than 0.1 electron volts. So we would end up, and considering the vacuum expectation values of Higgs fields, so we would end with the energy scale of 10 to 16 JeV, which is actually good scale. So which cannot be reached by other process. So with neutrino double beta decay, we can probe this good scale. The realization, we don't know actually, there are many possibilities whether this scale is just really good scale. People are considering that neutrinos, when there's a realization with type CISO1, so with right-handed neutrino inside within the great unified theories. So we have so-called CISO model, which explain the small, and to explain small masses, we need also to have very heavy Majorana mass. By diagonalization, we get very light and very heavy masses. But these very heavy masses can be not only on Planck good scale, it can be a TeV scale associated with LHC physics, at the Fermi scale or KV scale. All these possibilities are still open. So, so that new physics is associated, or the mass neutron masses are generated by 5-dimensional operator already mentioned by Steve Weinberg. within effective field theories, but the possibility that neutrino is Majorana particle was first introduced by Ettore Majorana in 1937 and was also discussed by Brune Pontecorvo when he first mentioned the possibility of neutrino oscillations. To see this process or to confirm that neutrino is Majorana particle, that means mass is, we need the Majorana mass term in the Lagrangian. People are looking for a signal of neutrino lambda beta decay. So we have nucleus with charge is increased by 2 units, and it is compensated by emission of 2 electrons. This process was introduced by Fury. It's analog with real neutrinos by Rakach. So this process has been not seen yet. People are looking for this process for a peak of sum of energy of 2 electrons. So if this process is realized, so kinematically, both electrons are taking the whole energy because we can, to a good approximate, we can neglect the nuclear recall in this process, which is very small, not measurable. For the as background for the process, we have 2 neutron lambda beta decay, which have the first observed in 1987, but already confirmed for 12 isotopes, even for 2 transition to excited states. And in this case, we have continuous distribution of energy of neutrinos because we have 2 additional antineutrinos emitted. The half-life of this process is generally, in the case of exchange of light neutrinos, neutrino-3 light neutrinos, is given by the effective Majorana mass, by nuclear matrix elements for the process, and some kinematic factor which is associated with phase space factor. Is well understood. This matrix element is a problem, cannot be related to other phenomenology, and the matrix have to be calculated by the tools of the nuclear structure theory. An open question is also the effective value of axial vector coupling constant. So this effective Majorana mass terms depends on 7 parameters, from which 3 are unknown. They are the CP Majorana phases. I would like to maybe it will come in later. Okay, it is given here. So we have these 2 additional Majorana phases in the case of Majorana neutrinos, so-called 2 Majorana phases. So they enter in this effective mass, Majorana mass. So it is a combination of the elements of mixing matrix and masses, all 3 masses. So we don't know 1 mass and 2 Majorana phases. So 2 Majorana phases one can consider as arbitrary, and then also one can do plot this quantity as function of the lightest neutrino mass for the case so-called normal and inverted hierarchy. So normal, that means we have the small mass square difference is down in the spectrum, and inverted, that is small mass difference is opposite. So we distinguish normal and inverted hierarchy of neutrino masses, or inverted spectra, normal spectrum, inverted spectra. And we found 2 possible solutions, which are indicated by blue and red regions. So one, we would measure this quantity. We would, additional information, we would allow us to determine the mass spectrum of neutrinos. We have also additional information relevant for the absolute neutron mass spectrum. It is the it concerns the sum of 3 masses of neutrons, which are measured in cosmology. These constants are very model dependent, and so the most stringent limit is that the mass of 3 masses is less than 0.1 electron volts. Also, from single beta decay of tritium, we can get such information, but it is not so stringent yet. So there are many nuclear systems which offer possibility to study neutron's double beta decay. The most favored are those with large Q value and natural abundance. Now, so all these nuclear systems were considered. There are different techniques from bolometer, trachocalorimeter, some TPC chambers, and with some crystals and so on. Liquid xenon, and the most important issue is just to have a lot of radioactive, pure radioactive I would say element, which can be the most interest is paid to germanium, molybdenum, tellurium, xenon. So there is possibility to large enrichments. Now the experiments are of the order of tens of kilograms, even 100s of kilograms. Few years ago, it was only just few kilograms. Very important characteristic is the resolution, because to see this peak, we need very good resolution of the detector or of the detector technique. And currently, the most stringent constraints of the effective mass of Majorana neutrinos is given here from all this experiment. You see the most stringent is from the EXO and Gerda experiment, even Cuore. Most stringent characteristics Kamlanzen, but they are comparable, Cuore, EXO, and Gerda. About 100 milli-electron volt. People are now preparing a new generation of experiments, so-called now 100 class kilograms experiments. Some of them are already running, and additional important parameter is is the background. So to eliminate all possible signals which can simulate signal of the observation of neutron's double beta decay. So it is not easy task. One has to go to the background, to the underground laboratory, and to do shielding, again mostly again cosmic muons, neutrons, and so on. So the most string element we have currently from the Kamlan then 400 experiment with 100 kilogram of xenon, 136, and Kamlan then 800 kilogram of xenon. So by combined analysis, one got this constraint which is given here. There are also in preparation Legends 200 experiment. And there is perspective to go with Legend experiment up to with 1 ton of enriched germanium 76, and the perspective is to reach even the region of the normal hierarchy. Another type of experiments are bolometers by low temperatures. Improvement of bolometers are it was a core experiment, was with bolometer with tellurium. Cupid experiment is just core experiment with particle identification, which allows better to reduce the background. And so this type of technology is also very perspective for future. In xenon experiment, there are 2 EXO and NEXO in US. Additionally, EXO in US, and Kamlanzen is in Japan. With NEXO, they plan even to use a few tons of enriched xenon. So you can see now that with this NEXO, one can come to the region of normal spectrum or normal hierarchy for this parameter M beta beta, and we can exclude practically the inverted hierarchy of neutrino masses. So the most perspective experiment for observation of neutron alpha beta decay are legend, qubit, and exo. But it might happen that not these 5-dimensional the exchange of light neutrinos and that masses are produced with this 5-dimensional operator. This mechanism is responsible for the neutron alpha beta decay. There is so-called Schechter-Wallee theorem. When we have any mechanism of the neutron alpha beta decay, we have to always change d quarks to u quarks and to produce electrons. And when we connect this line, this vertex, these two vertices, we get some radiative contribution to the Majorana mass, which can be small, but is saying that if we have any mechanism of neutron beta decay, neutrino is Majorana particle. But its mechanism can be different. So even if we are in the region which are not indicated in blue and red, we can have other mechanism, and this process can be observable. That can be not only relevant for neutron beta decay 5-dimensional operators, it can be also 7-dimensional and higher dimensional operators. We discussed the possibility to generate neutron masses with 7-dimensional operator, which is given here with two lepton fields Higgs and the two quarks fields, and after chiral symmetry breaking via the light quark condensate is produced, we get this dependence of the neutrino mass, and analysis shows us, because we know what is the value of the condensate, shows us that in that case this new scale in physics related with the Majorana neutrinos can be at the in the region of few TeV. So can be related even with the physics at LHC. In this mechanism, when we have 7-dimensional operator, we can generate these neutron masses. We can still have the exchange of light neutrinos, and we have contribution to the light neutron masses. But we have a separate mechanism which actually dominates and which allows us to put constraints on this coupling, which is unknown. But putting all these two diagrams together, we find out that it is possible only if there is a normal hierarchy of neutron masses, and the contribution from the lightest neutron from this region very strong cancelling. So it allows us to suppress this contribution and put it in correspondence with the strength of this mechanism. But in that case, we can say what are the masses of neutrinos, or what can be predicted from the measured in cosmology, and what one can see in tritium beta decay experiments. So under this assumption of neutron mass generation, we have clear results for the neutrino masses and for the hierarchy of neutrino masses. Of course, there can be other mechanisms. One favored is that we have, in addition, one heavy neutrino, and which coupled to electron neutrino with this element of the mixing matrix. And then if we assume this contribution from this heavy neutrino is the dominant one, it can be cancellation of the or suppression of, as I mentioned already, the contribution from 3 light neutrinos. So then we have to consider the mass of neutrinos in neutrino propagator, which in the case of light neutrons can be neglected. But when this mass can be in kV, MeV, TeV, GeV scale, or even higher, so it plays a role. Two asymptotic case is that, so now the matrix elements depends on the neutron masses of this mass. In the case this mass is small, below maybe MeV, we get just expression with for the definition for the mass matrix element associated with exchange of light neutrinos, and if it is very heavy, maybe TeV, even tens of JV. So in that case, we have a definition of matrix element of for the exchange of heavy neutrinos. And there are these two limiting cases. These two limiting cases allowed us to write the half-life for this process with such interpolating formula which imitates the behavior of the neutrino propagator. So and this quantity can be, which is just effective exchange momenta, is given by this expression, so can be calculated by calculating corresponding nuclear matrix element in two limiting cases. And when it was used, one get constraints on the use the fact that this process has been observed. We are considering the half-life limit, so the lower limit on the half-life of neutrinos on beta decay. In that case, what we get, what is about here, 10 to 26 here. Everything above is excluded in this plot of the mixing of the element of this heavy neutrino, independent of the mass of heavy neutrino. So everything above is excluded. So we get more significant constraints on these heavy sterile neutrino as from other accelerator experiments or from other even Catherine and so on. And by increasing the sensitivity of the experiment with to the half-life 10 to 28 years, so we come to this region. Now, of course, one can extend this model. One can think about left-right symmetric model of grand unification. So in addition to the left-handed current neutrinos, we have right-handed neutrinos, and then also left and right-handed current interactions. In that case, the mixing matrix will be not 3 by 3, what was this case, but 6 by 6, and we can be defined by 15 angles and 15 phases. What is actually a problem? Yes, the relevant left number violating parameter is given here, which take into account the interpolating formula, and this effective momenta practically doesn't depend on the nuclear model. It's practically the same for each nuclear model. In each nuclear model doesn't depend on the nuclear element. It's practically the same. So in that case, it is just shown here that this quantity for different nuclear structure calculation, interactive shell model, IBM model, QRPA, projective Hartree-Bogoliubov, then density functional approach. So practically is very small spread when taking account for all isotopes. So can be considered that it is not measurable, this difference. So to analyze this scenario, we simplified and used the seesaw structure. In this case, introduce only one seesaw parameter which connect the light sector and heavy sectors. And for such a matrix, we find out that this mixing for heavy neutrons can be determined by the unitarity condition, and this matrix is just Hermitian conjugate of the PMNS matrix. So instead of these 15 plus 15 parameters, we have just like before, 3 mixing, the 3 phases, 3 masses, but plus 1 CP of 1 seesaw parameter. The corresponding in the molecular violating parameter associated with exchange of light and heavy neutrons are given here. It can be inverse. One can assume that the masses of light and heavy neutrons are inverse proportional or just proportional, additional assumption. But then one can analyze the contribution from heavy neutrons related to the lightest neutrino mass. And one find that from heavy neutrino, this contribution, which can be compared with M beta beta, can be in the region of current experiment. So these two mechanisms can be comparable. So it might be that exchange of heavy neutrinos dominate, or it is not given here. So as we see, currently the limits are of the level of 0.1 electron volt for this quantity. So there can be some region, and to discuss this problem, we need additional information from particle physics side, from other phenomenology, maybe muon to muon decay of to electron and photon, and some other related lepton flavor or lepton number violating processes. Lepton number violating is a little bit problem. Lepton flavor there are which are also relevant. Now, are there other possibility to look for the lepton number violation? We address also the problem of the oscillation of neutron antineutrinos when also the lepton number is changed by 2 units. But this process is governed with also with some effective mass, which is given here, but which depends on the distance of propagation. So it is the same parameter like in the neutrino beta decay, but for with some L. When we put L equals 0, we just get originary parameter. So we address the question, what happened when we are unlucky and neutron beta decay is strongly suppressed because the lightest neutron mass is from this region. So we found out that by oscillation from neutron antineutrinos and taking different parameters of L over E, if there is full cancellation for this parameter, we can come out of this region. So maybe one can analyze some possibility for detection of an oscillation of neutrinos to antineutrinos. It is the same, but as parameter over E when it comes from the upper bound and lower bound in this region. People are looking for Majorana nature of neutrinos. These processes generated by heavy neutrino, which is right-handed. So we can have a decay of right-handed vector boson, which does exist in left right symmetric models. And here is the diagram. So you can see we produce lepton, then heavy neutron is also produced, but which decay further and produce additional leptons. So people are looking for 2 jets and 2 leptons. And already they excluded these regions, which are given here. And neutron double beta decay exclude only less region, you see, because everything down is just excluded by neutron double beta decay. So with improving, we can improve this limit. So there's a chance that one can see signal of Majorana neutrinos at LHC, and it will be not possible with neutron double beta decay. If this lepton number violating energy scale is just at a TeV scale. As byproduct of the measurement of neutron beta decay is the measurement of the 2 neutron double beta decay. And so one can look for different phenomena which have different energy distribution of emitted electrons. So the standard is given here, but there can be processes like with emission of Majoron, 2 Majorons, 3 Majorons, even more Majorons, processes generated by Lorentz invariant violation with bosonic neutrinos. So they have additional different behaviors. So we would have small contribution of different spectra on background of the main contribution. People are looking for such a bump and put constraints of the unknown parameter related with this lepton number violation, myorons, or bosons. We also discuss the possibility of observation of sterile neutrinos with masses in MeV range with 2 neutron alpha beta decay. You see if there is some mass, it's in the case of 1 MeV of heavy sterile neutrinos, so we have, due to energy conservation, the spectrum on it earlier, and putting two together, we can have small signals. So people are looking for such a contribution here. One can also constrain the parameter of right-handed currents in this way by studying the angular correlation of emitted electrons. The process which can do it very well is just the Superconducting experiment, which is in construction. It will contain about 200 kilograms of enriched selenium. And what is nice in the experiment, they will see tracks of both electrons. And the reconstruction from the tracks allows to conclude, and they will have about 1 million of events. So with this statistic, one can study all these exotic phenomena, all these fine contribution to the full spectrum. So this experiment is in construction in modern underground laboratory. Now about the problem of nuclear matrix elements. So as I told you already, nuclear matrix element of double neutrons of beta decay have to be calculated. In 2004, there were big uncertainty. People were astonished when they realized that factor 10. Now the situation is better than factor 2-3, and there are more advanced nuclear techniques are used for calculations of the nuclear matrix element. And in addition to the nuclear shell model, QRPA, Project IBM, energy density function, people are trying to calculate them also with ab initio calculations, with some green function approach, and so on. So there is a big progress. And why is it complicated? Because we need to construct wave function of initial final nucleus in ground or final in excited states, and all states of the intermediate nucleus. And in addition, we have to well formulate the nuclear transition operator and to have some feedback for the symmetries, because we know that these 2 ground states belongs to different isospin isospin multiplets. So there is change of isospin by 2 units. And isospin is more or less a good concept in the transition. So you can see current situation with nuclear matrix element with different nuclear models for light and neutrino, the for matrix elements associated exchange of light neutrino with heavy neutrino. So especially for heavy, there is larger spread. Some of models cannot do it well because they have very limited model space. New phenomenon is that Vincenzo Cerniciano looked on the amplitude of the process of changing 2 neutrons to 2 protons to make it renormalizable. He found out that to ensure it, that there is need to add some contact term. And this contact term was not calculated before, is given here. And so in addition, with standard contribution with neutral potentials, with Fermi, Gamow-Teller tensor operators, we have this calculated. This is due to some moment dependence of hadronic vertex. So there is this new delta function operators. And it was calculated or estimated in the QRP nuclear shell model. And they found that it can be as important as all the previous calculations. So it is up to 70%, you can see here in the QRPA, up to 60% for different nuclei. So this problem is not solved or understood till now clearly, and maybe some improved calculation are needed. To explain the problem of calculation, or to get the reliable nuclear matrix element with small uncertainty, we need a cross-check with of the used wave functions, nuclear wave function, with other processes like beta decay, double beta decay, muon capture, pion double charge exchange reactions, and nuclear and heavy ion double charge exchange reactions. So here you can see the multiple decomposition of these matrix elements for light neutron exchange, heavy neutron exchange as function of the multipole. So one can populate all possible multipole because we have full set of virtual states. If we have a large model space, so they slightly differ, and you see when the transition through 2- states is very important. So all multiples have to be considered, and to study such transition through interminescence, we have to populate them, and we can populate them with muon capture, with heavy double charge exchange reaction, and with pion exchange, and with charge exchange reaction. So to one level, and so therefore we need them to have confidence about the calculation. Of course, we have already the most important currently cross-check is with 2 neutron double beta decay matrix element, which this process was already measured. The corresponding matrix elements is here. 2 gamma-Teller matrix elements with energy denominator, because we know there is a second order process. So the matrix element experimental values are indicated here. So we see there is no pure difference. So dependence is different from that we know, which is calculated for neutron double beta decay. And in 2 neutron beta decay, there is interesting phenomenon that it seems that only the low-lying states, or there is a dominance of contributions from low-lying states. Whether this dominance works also for other multiples, we don't know. It's also subject of study. This was confirmed already by energy distributions of the emitted electron in the case of so-called single-state dominance, and highest and decimal difference. So there are experimental indications, like by Nemos 3 experiment, that there is single-state dominance. You see his score is much better here as here. The additional problems is just of quenching of GA. We don't know this value. Some calculation shows maybe for free nucleon is 1.27, but there are some indication that for maybe due to nuclear structure calculation, maybe because we have nucleons in a medium, this quantity can be much smaller, even 0.6. What can be a catastrophe, because half-life depends in fourth order on this quantity. But there was some analysis, Nature paper, studied single beta decays in effective theories, and so they are saying that if we consider 3 nucleon forces, 3-body nucleon forces, and just 2-body exchange current, so in that case we don't need quenching of GA. So quenching of GA can be also studied with muon capture, and there are some contradictory results. In this publication, they explain the measured half-lives for this process with GA with 0.6, index 2 is 1.1. So we calculated also this quantity and found out that is not needed, only modest quenching is needed. It was a good message. Consider large, big model space, everything. So you see these measured quantities, and here are the calculated with small model space and very large model space. So so we agree with these two calculations, not with the third one. Well, we believe it is very important, and not only with the field of the whole community, to study heavy ion double charge exchange reactions. So in this heavy ion, one can simulate transitions with change of nuclear charge by 2 units, with this, for example, coming from selenium to germanium, with having ions of oxygen 18. In the end, we produce 18 fluor, or coming from this to this direction with 20 neon. And so these measurements are on the way. Of course, there are some additional, one can, by this type of heavy ion reaction, okay, other possible channels opening, but they, people in Catania already proved they can clearly measure, clearly measure just the transition to the ground state, and there is only small strength goes to this, but it's very important to cross-check calculation of Newton's double beta decay matrix elements. So they are now improving the setup, and that will improve the measurements, and now is the formulation of the theory of these heavy ion reactions. It is just Horst Lenske in Bochum, and new measurements and new calculation are on the way. So to solve the problem nuclear matrix element, we are just at the beginning of the road, and we need to get the reliable nuclear matrix element. We can consider all these symmetries or use data from different supporting nuclear experiments. So to complete information about neutrons of beta decay, here is a list of some reviews, recent reviews. So there are many of them discussing particle nuclear physics aspects of this process. And you see, it is so that in the mankind, there are some problems, and it takes a long time to solve them. I would just mention one that about around 1637, Pierre Fermat wrote in the margin of a book the more general this Pythagorean equation, and saying that for n equal larger than 2 there is no solution. And this proof was already done only in 1995, after 358 years. So we are now 85 years after Majorana mentioned the possibility that neutrinos are Majorana particles. And all this grand unification theory, they need it, that neutrinos are Majorana. So if we can a little bit more understand what is happening in the universe and to how it's constructed with Majorana neutrinos, but we need a proof that the really neutrons are Majorana particles. There are many experiments which are ambitious, and they would like to see signal of this process. But after it can happen, then after maybe we don't know how many years, we will not see the signal of this process, because if the effective mass is in the region below 1 MeV, we don't have technology for it. So so we will then, now this problem can remain, and one has to look for other possibility to solve it. So this was my last slide, and thank you for your attention. And let's hope that we will observe neutrons double beta decay. Maybe even with help of this next generation of neutrons double beta decay experiment, like Legend, Nexo should be, or Camland, Zent, or others. Thank you for your attention.
Yeah, let's hope we can observe it. Thank you very much, Fedor, for this very interesting talk. Is there any question?
Okay. Yeah.
Please go
No.
ahead. Sid.
No, yeah, I raised my hand.
Okay.
May I ask?
You can ask.
Yeah, Fedor, thank you very much for your interest and excellent talk. And I would like to ask you a few questions. The question about heavy ions reactions. What did you mean? What reaction is? Collisions or what? In which
Yes, so we have target,
collision?
yes, we have target which is just isotope participating in double beta decay. It can be
Yeah.
selenium or germanium.
Mhm.
We have a beam of oxygen 18 or just of 20 neon. And with this, we can just measure this small transition here, which is relevant for double beta decay. So,
then, so this is a collision or fixed target experiment.
It is a collision, yes.
But collision, I mean, this is
Nuclear
a fixed.
collisions.
Yeah, right. I understand. But this is a fixed target experiment with a fixed target
Yes.
and
beam.
and the beam. Okay, launch it onto the target.
Yes.
Okay. Yeah, I see. Okay.
And so you see in two neutron beta decay is dominated with transitions through 1+ state of the intermediate nucleus, but it's not the main contribution to the nuclear matrix element. So here we will populate also these states. Therefore, it's considered to be important for this type of transition. But actually, it's a complex process, and the formalism would include matrix elements which are somehow similar to two neutron beta decay, and some of them to neutron double beta decay. It is like when we have pion double charge exchange, one can have pion vertices due to pion P wave absorption on nucleon. And then one can have also when you produce intermediate pi zero. So there is also.
What is the energy? Yeah, I see. And what is the energy of the beam?
There's few hundred MeV. So the momentum transfer corresponds to that. Is comparable with the neutrino momentum by neutron double beta decay.
So then the nuclear do not fragmentate. There is no fragmentation.
There is no.
I see. Yeah,
so you see, you can measure transition to the ground state. What is it? What is all?
I see. Yeah. Okay. Of course. Yeah.
But you can have the region of gamma terrain resonance, which is also there. Everything is interesting from the point of nuclear physics, but this transition is for neutron double beta decay. And there are about 3 institutes which are planning or doing this type of measurements. So there is in Riken, in Japan, in Catania, and by Michigan. There is also.
Yeah. I see. And about Super Nemo experiment, when it is expected to start taking data?
So maybe it was planned end of this year, but I think next year.
Okay. Yeah. Okay. So thank you, Fedor. Maybe somebody else has questions.
Yeah, I do have a question.
Okay.
Please, Fedor, can you go back to that slide which you showed the master formula for neutrino oscillations?
Okay. Yes. I'm glad you are interested in this subject.
Yeah, I think it's very interesting to try to formulate this in quantum field theory.
It is.
Yeah, I was wondering what kind of corrections do we have from this formula to the non-relativistic quantum mechanics treatment, and if we can hope to observe this in an experiment some deviations from the quantum mechanics treatment.
So that is question of our study, what we are now discussing, but it seems that all additional effects are related with the mass of neutrinos. So if there is some heavy neutrino in the propagation, so one can, you see, you can, it is not just this expression only for propagation of light neutrinos, it can include also heavy neutrinos. So if the mass of the heavy neutron is large enough, so one can see some effect, but for light neutrino, it seems to us that by all these processes with the relativistic reactor, atmospheric, and so on neutrons, one can neglect them.
Okay.
You see, in this we get, you can compare, this is the standard formalism. In this blue and violet is just what we get, compare these two quantities, and we have some additional contribution from due to neutrino momenta.
These momenta are from the neutrinos.
Yes. So you see, energy is conserved, energy is fixed at the source and the detector, and this is just momentum is square root of the energy squared minus mass of the, okay? So mass is appearing here. So we were not doing this expansion, which is already done here. So it should be done still.
I see.
Yeah, maybe I just make an extra comment on this point, because this study is not only about the numerical effect. It is about mainly about foundation of this process of neutrino oscillations, because quantum mechanical interpretation is has many loopholes, many questions about its foundation from the viewpoint of, for instance, it is non-relativistic, right? And it is hardly applicable to heavy neutrinos, as Fedor said. So then this is mainly about how to formulate this process in quantum field theory. Yeah, just to comment.
Yeah. Okay. One follow-up question. In the quantum mechanics formulation, you can imagine this process as like separate processes, the production, and then the neutrinos propagate, oscillate among each other, and then they are detected.
So this is a standard quantum mechanical approach. So you produce neutrinos, yes, and you take it as three separate processes. Then you propagate neutrinos. You just consider plane waves. That's the quantum mechanical approach. And then you absorb neutrons. So there are three separate processes, but which are not related. If we have just this field theory approach, we have neutron propagator, and we are coming lepton currents, and one has to calculate the probability. So one has to calculate traces. So therefore, some additional contributions are appearing. And but still, there is still this problem. You see, we have to get this, that we have two, the energy conservation we got because of this integration of energies, x10, x2, no, about the time component of the coordinates, x10, x20. So there is energy conservation immediately. But then playing with this propagator first, we found out that this pole, which is given in, guarantee the energy conservation of the source and detector. So the really neutron which is produced in the source has related with the first process and second with the second process. But this approximation allowed to get also momentum conservation, because we separated plane waves. You see this approximation, we get here plane waves of neutrinos. And it due to that fact, we, or maybe better saying, due to these approximations, this contribute to plane waves, it is from the propagation. And we get to momentum conservation. But the price is that coming, so on the level amplitude everything clean. Coming to the master formula, we have to normalize these delta functions, these plane waves. And we have two normalization with the source and detector, and which are here. So in this way, everything is okay up to the, here are two different momenta. Up to difference, due to this normalization to the source and detector, up to the difference of masses of neutrinos relative to the energy, which is small quantity, and really these normalization volumes of the source and detector are large. So therefore we assume at least for light neutrinos it's okay. For heavy neutrinos one should discuss, but we can also heavy neutrinos with small mass difference, which is also okay.
So you have to consider the full process. You cannot factorize, but in this approximation you can get some sort of factorization. You have independent
there is no
energy
factorization.
conservation.
No, there is no factorization. No.
There is, okay, but
Then
you
in
have
quantum,
separate conservation of energy in the source and in the
Yes.
detector.
Yeah.
Yeah.
So this is a result of quantum field theory. There is no factorization, contrary to the assumption of in which is based the non-relativistic quantum mechanic treatment of this process. So there is no factorization.
Okay, I see. Is there any other question?
Okay.
It seems there are no more questions. So let's thank you again, Fedo, for this very interesting talk.
Thank you.
Thank you all for attending this SAFE webinar. And we'll see you again in the next SAFE webinar next month.
Yeah.
So thank you all. And
Guys, thank you.
Bye.
Thank you for
Bye.
attendance, and
Thank you, Pedro.
have a
Thank
nice
you,
day,
Pedro.
nice
Yeah,
weekend.
you too.
Bye.
Yeah. Bye.